coming from water. This oxygen is coming from the air we breathe. Okay, that's important to note.
So this all just the shuttling slide of electrons.
Yep.
Okay.
Yep. But what's it actually doing? Like, okay, so we're passing electrons down a chain. How does that turn into energy? So this is where chemiosmosis comes into play. Okay. So this is just a few more notes, and then we'll talk about chemiosmosis. So it's just pointing out the electrons get transferred either from NAD or FAD to the electron transport chain. It's talking about there's all of these proteins that include cytochromes. Those were those CYT proteins. And the cytochromes are unique because they have an iron atom in them, which is a little heme. They have a little heme group that attaches to an iron atom. About to sneeze. Now it's in the past. Well, you know that weird sensation in your nose. Okay. Oh, it's so good. All right. All right. So we still don't have any ATP. All I've told you is like I've taken electrons and I've gotten you all excited. This is where we're getting all our ATP. But you didn't see any ATP come off of that chain, did you? No, you're just like, okay, so we passed the electron down. That's great. Where's the ATP at? So that's what we're going to talk about next. So what we're doing is that a lot of these little protons or proteins along the way that are embedded in this multi-protein complex, what they're actually doing is that as the electrons pass down, there's a little bit of energy released, and they're using that energy to pump protons into this intermembrane space. So we're getting a big buildup of protons out here. That's what, so we've got all of these little protein complexes lined up end after end in the cristae of the mitochondria. And as the electrons are falling down the electron transport chain, little bits of energy are released. And some of these little proteins that are embedded in these multi-protein complexes are using that energy that's released to create a concentration gradient. Do you guys remember concentration gradients from chapter 8, that we can use concentration gradients to do work? Same way, like if you think about water is up here at the top of the mill, it has potential energy. You release that water, it can run over the water wheel, turn the water wheel, and create the ability to do work. We are creating essentially the same thing here. We're creating a concentration gradient where we have all of these protons, and we're going to let these protons fall down their concentration gradient through this cool protein I'm about to tell you about to actually do work. Okay. Okay. So here we are with this idea of chemiosmosis. So what we're really doing when we're transferring these electrons is that energy that gets released as we move the electron down the transport chain is allowing proteins that are embedded in that chain to pump protons into the intermembrane space. Do know that it's the intermembrane space where the protons are being pumped. They're not being pumped into the mitochondrial matrix. They're being pumped into this intermembrane space. There is only one way for these protons to get back into the matrix, and it's through a protein called ATP synthase. And I'll tell you about it in just a minute. Okay, so protons are all here. They're all dying to get into the matrix. Remember, molecules want to be at a lower concentration gradient. They want to passively move from an area of high concentration to low concentration. But these guys only have one way through this inner membrane. So we're going to use this really cool protein in order to allow the protons to fall back into the matrix. And again, it's called ATP synthase. And then just an overview of what we're doing here. This ATP synthase protein is using the exergonic flow. Exergonic means energy releasing flow, because when things move down their concentration gradient, they can release energy. So this flow of protons back into the matrix to phosphorylate ATP molecules. So how do we do it? And then this is telling you that chemiosmosis is where we're using energy to drive cellular work, but that's what that term refers to. So this is how we're taking the electron transport chain and turning it into something that actually does work. This is the cool protein that I was telling you about. It actually has like a real working rotor. So this is what happens. We're in the intermembrane space out here where there's a bunch of protons, right? They all want into this mitochondrial matrix inside here. There's only one way. They are not allowed into the mitochondrial matrix unless they fall through this ATP synthase protein. This is how it works. There's several different parts of the protein. Remember, you can put multiple subunits together. This is called the stator. This is called the rotor, and it turns. The rotor is attached to a rod, and the rod is inside this catalytic knob. And so the proton falls into the top of the stator, and every time it falls in, it attaches to the rotor, and every time a proton attaches to the rotor, it causes it to move in a circle, just like a water wheel. So every time a proton attaches, losing track, the rotor keeps moving around and around and around. And so the proton's going to fall in here, attach, and then it will move and make an entire rotation around the rotor until it gets back to the beginning. And when it gets back to the beginning, there's a little space where it can fall, and now it's in the matrix where it wants to be. But what's happening is that as this rotor is turning, it's attached to this rod, and this rod is also turning, and in turning, it exposes all of these sites on this catalytic knob, and this mechanical turning is what's allowing our ADP and our inorganic phosphate to regenerate ATP. So this is not substrate level phosphorylation anymore. This is, what was the term that I was using? Oxidative phosphorylation. So we're using that energy that we generated from the electron transport chain to create a proton gradient. And when those protons fall back down into the matrix, they turn this mechanical rotor, which generates mechanical energy to allow ADP and inorganic phosphate to rejoin an ATP molecule. 28 ATP molecules per molecule of glucose. Okay? This is how we're doing it. Have you guys learned about this molecule before, this protein? Yeah, I always found it so frustrating when I was in high school and they were like, it's the electron transport chain. I'm like, I still don't understand how that makes ATP. It doesn't make ATP. It creates a protein or a chemical gradient, which when the chemical gradient is restored as the protons pop back down and jump back into the matrix, they turn this rotor, just like a water wheel turns. And when the water wheel turns, there's something attached to it that's also turning, and it turns this this rod. It moves inside of this catalytic knob, and the catalytic knob is going to catalyze the synthesis of ATP from ADP and inorganic phosphate. Yes.
So there's just a bunch of ADP just waiting for extra phosphate inside of the matrix?
Yeah.
Okay.
Yep. Okay, so here we're looking at it all kind of, now we're looking at the cristae, the inner membrane of the mitochondria. This is the inner membrane space, and you can see how we have all of these multi-enzyme complexes lined up, 1, 2, 3, and 4. The NAD, where does it donate its electron? Which is it donated at number 1, number 2, number 3, or number 4? 1, yes. So it starts at the top, so at the least electronegative. FAD donates its electron at the second multi-enzyme complex. And this is where we have all of those proteins and those cytochromes, and we're going to pass the electron down the electron transport chain. And as it gets passed down the electron transport chain, energy is released. We use that energy to move protons into the inner membrane space. We still don't have ATP, but we have a concentration gradient. And we use that concentration gradient to generate ATP, because as the protons try to get back into the mitochondrial matrix, the only way they get in is by going through this protein called ATP synthase, which is that really cool rotor that moves every time a proton attaches, turns the rod, which turns inside the catalytic knob and uses mechanical energy to regenerate ATP from ADP and inorganic phosphate. And so then we keep this constant supply of protons now that we can keep pumping them out, keep creating a concentration gradient as long as oxygen is available. Okay? No oxygen, you can't do this. Okay. So when you guys were eating your food, this is what was happening. This is how we're actually getting the ATP. You know, you might feel sleepy right now. After a little nap, you want to go for a run. This is where the energy is coming from. So you're turning that sugar energy into actual mechanical energy, because the ATP can now be used to do that mechanical work or that chemical work inside your cells. When you talk about muscle physiology, you'll find that ATP is responsible for allowing the myosin. Remember we talked about, well, we didn't talk about it, but muscle contraction is an interaction between myosin and actin, and it's ATP that allows the myosin to move back and forth. And so if you don't have ATP, your muscle doesn't contract, okay? ATP is our energy currency in the cell.